So this is chapter 7. We actually broke chapter 7 into two halves, all in the same PowerPoint. But the reason we broke it into two halves is because it's kind of two very separate topics. The first half, we will go over ionic compounds. We'll spend a lot of time on that. The second half, we'll go back to moles and mole conversions. And the second half deals more with moles. So the first half here's what you should be able to do after you watch the videos for the first half of chapter 7. You should know what ionic compounds are. You should be able to assign oxidation numbers to the elements in a compound. And you should be able to name and write ionic so it'd be able to name ionic compounds and write their formulas out. So the first thing we're going to start with is oxidation numbers in chapter 7, or oxidation state. It is simply the charge that we give atoms to basically show how electrons move around. So it's assigned to atoms in a compound to show the distribution of electrons. You have some of the oxidation numbers listed on the top of your periodic table. So if you go group 1, 2, and then it skips through 13 through 18, you got that pattern: +1, +2, +3, plus or minus 4, then -3, -2, -1, and then noble gases don't have a oxidation number. That kind of tells you, that helps tell you whether the atom likes to gain or lose electrons. But you might be wondering, like, well, what about the transition elements? They don't have any oxidation numbers. That's what we're going to get to today. So it tells you how many electrons are gained or lost. Remember, if you lose electrons, you become positively charged. If you gain electrons, you become negatively charged because electrons are negative. And we call a positive ion a cation. A negative ion is an anion. So just some review terms there. This one, a polyatomic ion. Write this down. It doesn't mean a whole lot to you now, but we'll explain it more in a second. I'll explain it more. And we'll start using these pretty frequently now. So a polyatomic ion is a group of atoms that has a charge. It behaves like a single ion, but it's made of a group of atoms. So it's kind of weird. It's a group of covalently bonded atoms that has a charge, and it behaves like an ion. So it's a little bit goofy, but you'll get used to them pretty quick. So the overall charge is found on your yellow sheet. I'll show you that in a second. The rules for assigning oxidation numbers are also on your yellow sheet. So let's get to those. So you should have your yellow sheet out. If you look in the top of the page, here are the rules. The rules for assigning oxidation numbers. Follow them in the order that or apply them in the order that they are written. So you might have a compound where two rules apply and they contradict each other. You follow the top rule first. That one gets priority. So one thing, the first rule is if an element is uncombined, its oxidation number is 0. Fluorine will always be a -1. That never changes. Hydrogen is usually, so this is where it gets a little tricky. Hydrogen's usually a +1, oxygen's usually a -2. Now, however, if you have a compound that has hydrogen and oxygen in it, you may have to violate one of these rules, and if you have to pick which one to violate, you violate the second one. So if these two rules contradict each other, you go with rule 3, and then you violate rule 4. Well, you're not really violating because it does say usually. And we'll go over an example of that later. Now, number 5, halogens other than fluorine, so chlorine, bromine, iodine, they're almost always a -1. So you can just give them -1. And then for any compound, the oxidation numbers have to add up to 0. So that's another key part of this. Okay, so the top of your yellow sheet, if you flip it over on the other side, has a whole table of all the oxidation numbers of all the elements. So you might be like, well, why do we need the rules if we have the whole list of all their oxidation numbers? This is going to be super easy. But you might notice that some of them have multiple oxidation numbers. So that's where it gets a little bit tricky. So if I asked you to assign oxidation numbers and the compound has cobalt in it, well, how do you know if it's a +2 or a +3? And that's what we're going to show you. On the same page of your yellow sheet, you have the polyatomic ions. The polyatomic ions are listed here. This is their name. There's two sets of, so they're in alphabetical order. So you got half of them here, half of them here. There's two columns. Now the symbol, so for acetate it's C2H3O2, and then there's a minus because it has a -1 charge. So this group of atoms, it behaves like it's an ion. It kind of clumps together and it moves around and it never breaks up, and it has a -1 charge. So it's like it acts like it's a single ion, but it's actually a group of atoms that behaves like an ion. So that's all you need to think of it as. It's a group that kind of moves around and stays together, and it acts like a single atom you can think of that has a charge. All of them are negative except ammonium. It's NH4 with a +1 charge. So ammonium's the only one that will be found at the beginning of the formula, because you always write a compound. The positive ion is written first, the negative ion is second. So the polyatomics will mostly be at the end of the formula except ammonium. Okay, so let's practice. So we've got UF6. Now, here's all of our resources on your yellow sheet. I kind of pulled them together here so you can see them all at once. Now, the first thing I always like to do is, I know that the sum of all the oxidation numbers has to add up to 0. Now, in order for it to add up to 0, that means there has to be a positive and a negative half. And like I just said, the positive half is always on this side, the negative half is always on this side. So I like to split my compounds down the middle. Now they've got to balance. All the positives on this side have to equal the negatives on this side. They have to be equal, so that it adds up to 0. The positives and the negatives cancel out. Okay, so if I look up uranium first. I go over here, here's a list of all my elements. I go down uranium, and can be +3 or +6. Okay, that poses a problem here. I don't know which one it is. Okay, so then I look at fluorine. Let's just skip this one for now. It's a question mark. Question mark. It's +3 or +6. It's one of those two options. Now I look at fluorine. My rules over here. Fluorine is always a -1. And that's why if you look here, fluorine only has one option. So let's use the one that we know. So my fluorine is -1. So here's how I like to do this. I put a -1 here. That's my answer. Fluorine is a -1. But how many are there? There's 6 of them. Well, if each fluorine, let's go like this. 1, 2, 3, 4, 5, 6. If each fluorine is a -1, 1, 2, 3, 4, 5, 6. That adds up to a -6 charge. So you can put a -6 on this side. So all of the fluorines combined add up to a -6 charge. This is not my answer, but I need to know it so that I know that if this whole half of the compound adds up to a -6, this half has to add up to a +6. Because remember, our positives and negatives must balance. Now, if this half is a +6 and there's 1 uranium, that 1 uranium must have a +6 charge. So let's just recap there. Each fluorine is a -1. Because there are 6 of them, it must be balanced out with a uranium that has a +6 charge. These are my answers. Uranium's +6, each fluorine is a -1. But if I double check, 6 times -1 is -6. +6 times 1 is a +6. So I only use this to check to make sure that everything balances, but this is not my answer. These are my answers. So all of you put your answers on the top of the compounds. Let's try another one here. First thing I do is I split it. I look at iron. I find iron, it is +2 or +3. Okay, I don't like to guess. I mean, you could. It's a 50-50 shot. You get this right on the test, but you can do better than that. So you look at chlorine. Okay, chlorine. Oh, great. This is even worse. You're like, oh, no, what do I do now? Okay, when all else fails, go back to the rules here. It says, okay, nope. Okay, halogens. Chlorine is a halogen. Halogens other than fluorine often have an oxidation number of -1. So no other rules apply to this. So I take the first rule that applies and I go with it. My answer to chlorine is -1. Well, I have 3 of them. So -1 times 3 is, it's a -3. If this half of the compound is a -3 charge, this half has to be +3, so that means my 1 iron must be a +3. So out of my options, I picked the +3. So these are my answers. This is just to help me keep things balanced, because the sum of the charges has to add up to 0. Your answer doesn't have to add up to 0, but if you account for how many atoms you have, then it does. Okay, this one has a polyatomic. You know that because there's parentheses, that makes it pretty obvious. So I split it here. I check barium. Okay, barium. I missed it. Barium has a +2 charge. That's easy. You're guaranteed to get that right on the test if it only has one option. +2. Now there's only one barium, so I know that +2 times one of them is +2. I know that this half has to equal a -2. At this point, there are 2 of them. If the 2 chlorate, this is chlorate, it's, ClO3. Let's find it. So here's my polyatomic list. Chlorate. So here's ClO3. My 2 chlorates add up to a -2, so that means each one must be a -1. But I can also get that just from going over here and finding out that it's a -1 on my yellow sheet. So these are my answers. So you'll list your answers on the top of the compound. But notice that if you do check your work, +2 times 1 is +2. -1 times 2 is a -2. So they do balance, but these are my answers. Okay, Cl2. You might be tempted to go here and say, okay, chlorine has all these options. And then you look, well, halogens are a -1, but you skipped a step. Rule number 1 says oxidation numbers for any uncombined element is 0. So this is just 0. It's not combined to any other elements, so it's got an oxidation number of 0. Okay, try this one on your own. Pause the video. Okay, so I'll do it now. Hopefully you have paused and done this here. Na2SO4. This is a polyatomic. SO4. Nice thing about polyatomics is they only ever have one oxidation option. So this is a -2 charge. Now how many are there? That's the question. If it's a polyatomic and there's no parentheses around it, that means there's only one of them. So there's only one of these SO4s. -2 times 1 is a -2. A lot of people, when they balance this, they go -2 times 4 and say -8. This 4 does not tell me how many the 4 is a part of the SO4. It does not tell me that there are 4 SO4s. It's a part of it. If there's more than one, there'd be parentheses with a 2, a 3, and so forth. Sodium. If I look up sodium, where is sodium? It's a +1. +1. +1 times 2 is +2. I check, everything balances. These are my answers. Okay, let's try this one. Pause it, and then come back. Okay, iron can be +2 or +3. So I don't know. So let's go to nitrate. Nitrate is NO3. It is a -1 charge. Now there's 3 of them. Notice there's parentheses with a 3 there. -1 times 3 is -3. That means this side has to be +3. There's only one iron, so that one iron must be the +3 charge. So there you go. This one looks complicated, but it's actually quite simple. You just need to recognize that NH4 is a polyatomic, and this whole thing is a polyatomic. And then you go look, NH4 is a +1, and then acetate, C2H3O2, is a -1. So that is where we will end and we'll practice more in class.